So there's lots of different, there's an infinite amount of impedance discontinuities. I mean, any way that you change the transmission line. Let's say that this is just, let's say that this is a PCB. You have a trace on the surface and a return plane. If I were to change the width of this trace, just make it wider for whatever reason, that's an impedance discontinuity because you're changing the characteristic impedance of the transmission line. The characteristic impedance depends on the geometry of the transmission line. And so I'm going to talk about some pretty common types of impedance discontinuities. So let's say one is if you have like a certain transmission line here, transmission line, the same characteristic impedance, then you have a series transmission line discontinuity where there's like an oddball transmission line segment in the middle. And so this is the case that I just talked about. Like if you have a trace on a PCB, you just make it wider or you make it narrower or something, and then you just go back to the original width. So this is pretty much that case where you change the impedance of the transmission line in the middle. And as it turns out, the rule for whether this matters or not is the same as the in the previous video. So if the length of this transmission line is less than the rise time in nanoseconds, and the length is going to be in inches, then you have the whole thing with the re-reflections, and they cancel each other out, and this will be tolerable. You can allow, there's like a maximum allowable length of this transmission line discontinuity. So that's one type of discontinuity. You could also have a stub. So you would have a transmission line. Let me just draw this out. You would have like a transmission line branching out from here. And so I've drawn it as like a, I'll just leave it like that. We don't know what it's terminated in. So this could happen if you have like a multi-board stack, like a bunch of stacked boards that are connected to some sort of connector, like this, some sort of stacking connector, but you don't connect like one of the boards. You just sort of leave it floating there. Then all the traces going into that board, all of the connection from the other boards going into that board will be a stub, for instance. And so how do you resolve that? And actually, it doesn't even have to be disconnected at the other end. This could actually like be terminated at like an actual IC, and this could be terminated at an IC, and this could be terminated at an IC. It doesn't have to be like an open circuit. It's just this junction, that branching point, creates like these two branches, and so that's what the real issue is here, because you're changing the geometry of the transmission line at this point. You'll have your incident wave coming in, sees the impedance discontinuity, reflected wave back, transmitted wave forward into here. Then you see your reflection out of this end that bounces back up there. Then this new reflection is going to add more noise back at this original junction in the middle over here. Then this reflection will it'll just sort of rattle around within this. You pretty much just have this signal rattling around within this stub, and each time it hits the original transmission line, it just adds noise, and eventually it'll die out. But yeah, so that's kind of what the issue is here. And the way that you can tell if this will be an issue, again, same rule of thumb. If the length of this stub in inches is less than the rise time in nanoseconds, it would be allowable. And this is, of course, this is just a rule of thumb. It doesn't have it. I mean, we're making an inequality with inches on the left-hand side and nanoseconds on the right-hand side. So obviously, this is not mathematically rigorous. It's just a rule of thumb. I'm referencing Eric Bogatin, his textbook Signal and Power Integrity for this rule of thumb. So that's where you can learn more about how this was derived. Okay, so those are two types of transmission line discontinuities. What if you have a transmission line I'm just going to draw it as a single line just for simplicity. A transmission line with a capacitor in the middle. So when you have, this is referred to as a capacitive discontinuity for obvious reasons, because there's a capacitor in the middle and it's creating an impedance discontinuity. What you will see is this will act as a delay adder in the signal. So if the signal would originally, at this point, at this end, if the signal originally would have looked like this, now it's going to look something more like this. So it took longer for it to reach its actual value. Because, I mean, think about it, you're essentially just charging up this capacitor. Capacitors resist changes in voltage. It's going to push off that change in voltage for later, kind of like what a bypass capacitor does, except in this case, it's unintentional. And so you have this delay adder. Another way of thinking about it is it's acting as an RC filter, because you have like some resistance here and you have this capacitor. And then so it's filtering out some of those higher frequencies. And remember, like this square wave, the way you make a square wave, you just have, so it looks like this, you just have a certain DC component, then you add in a sine wave at the fundamental, sort of at this fundamental frequency of the square wave. Then you add in another sine wave, and I won't bother drawing this accurately, but you add in another sine wave at 3 times that frequency, another one at 5 times that frequency, then 7 times that frequency, and so on. And you just add up all these odd harmonics, these odd multiples of the fundamental frequency, and you just make that square wave as you keep adding those harmonics. As you start filtering out the higher frequencies, because the RC filter, it's going to filter out some of those higher frequencies. And the way that works is the capacitor acts as a low impedance to high frequencies. It allows high frequencies to go through. And so those high frequencies, you're going to sort of be going straight shunted through the capacitor to ground, while the lower frequencies sort of, they see a high impedance at the capacitor. So they just move forward. They don't want to go through that high impedance. Anyway, as you have this RC filter, essentially, you filter out some of these higher frequencies, and you do this process in reverse. You start taking away those higher frequencies, and all of a sudden, it starts looking more and more like a sine wave, like this. You sort of just have those rounded edges. And so that's kind of the issue with having capacitance on the transmission line. And this is sort of one of the limitations of, for instance, like a communication bus. If you have too much capacitance on the bus, you can cause this sort of degradation of the signal. And so this was just like a really quick overview of some of the common types of impedance discontinuities and the problems that they can cause.